Okay, we've got, looks like nearly 60 people in the room, and it looks like we've got folks represented everywhere from it being Friday morning to Friday evening, time for a pint. It looks like there might even be somebody who just crossed into Saturday, like past midnight on Saturday. So it's great to have you all here. My name is James Pustievsky. I'm the chair of the American Educational Research Association's Special Interest Group on Systematic Review and Meta-Analysis. And on behalf of the SIG, I'd like to welcome everyone to the first installment of our online seminar series on meta-analytic methods. We conceived of these seminars as a place for us to learn about advances in methodology, to help to disseminate new research, and to really foster conversation about the challenges of using systematic review and meta-analysis to inform educational researchers, policymakers, and practitioners. The full seminar series is it's going to run for the remainder of the academic year, and you can find the full schedule of talks at the link that I just dropped in the chat. You can also find us on Twitter at let's see, Mega, could you drop the Twitter link in to the chat also? And let's see. Also, if anyone is interested in participating in this seminar series as a speaker, please feel free to reach out to me. We've got the next couple of months of talks scheduled, but after that, I'm happy to take self-nominations. So don't be shy. So my zoologist colleagues tell me that if you've got a group of lions together, you call that a pride. If you've got a group of geese, that's a gaggle. And as far as I know, a group of statisticians would be called a sample, I guess. In today's presentation, we're very lucky to have a highly non-random sample of scholars who've been working together as a group on a challenging and very common problem in applied meta-analysis, which is how to handle missing predictor variables in meta-regression analysis. So we've got 4 speakers. I'll very briefly introduce each of them, and then we'll get right into the talks. So first up will be Dr. Terri Pigott, who is professor in the College of Education and Human Development and the School of Public Health at Georgia State. Then we have Dr. Karina Diaz, who recently finished her doctorate at Columbia Teachers College. She's now a research specialist at the University of Pennsylvania's Graduate School of Education. Then Jihyun Lee, who's a doctoral candidate in the Quantitative Methods program at the University of Texas at Austin. She's also on the job market right now. And finally, Dr. Jake Schauer, who is an assistant professor at Northwestern University's Feinberg School of Medicine. Each of these speakers will sort of lead the discussion for about 10 minutes, and then we'll follow that with a general discussion and opportunity for Q&A. We also have the Zoom configured with the Q&A feature. You should be able to find that down at the bottom sort of buttons of the Zoom interface. And you can use the Q&A to pose questions at any time, and our speakers or others in attendance might answer those questions even as the other presentations are going, or you can just register your questions there, and we'll try to address them during the Q&A. And with that, let me pass it over to Dr. Terri Pigott.
Great, thanks, James. You can go ahead and, so this is what we're going to do today. I'm going to talk a little bit, sort of set the stage for the rest of our discussion on missing data in meta-analysis. So I won't spend any time on this slide. Go ahead, Jake. One more. Okay, so I think all of us here are working in this field of meta-analysis, and we all know that every single meta-analysis we've ever worked on has encountered missing data. And what we're going to really focus on today is particularly missing data in the form of missing information that we want to use as potential moderators of effect size heterogeneity. And so the question we've always had, probably throughout the history of meta-analysis, is what to do about this problem. So in the past, we've used complete case analysis. So we've just used those cases that observe the moderators that we're interested in, or we've used something we usually call shifting case analysis or available case analysis. Next slide, please. And we'll talk a little bit more about those two methods. Jihyun will talk about that in a few minutes. So what to do? Well, we can draw on the long history of missing data methods in the statistical literature. And those methods for missing or incomplete data focus on the mechanisms for missing data, sort of what data are missing and why. And in that statistical literature, the appropriate method for analysis when missing data occurs depends on that missing data mechanism, on why the data are missing. And so just to review quickly, many of you know this, but there are sort of in that statistical literature, we talk about three major missing data mechanisms: missing completely at random, missing at random, and then missing not at random. So what I want to spend a couple seconds doing here is just talk about how those mechanisms might translate to the context of meta-analysis, and particularly into applications of meta-regression. Next slide, please. So again, we use meta-regression when we want to examine models of effect size heterogeneity. And in everything we're going to be talking about today, we're going to assume that we observe all of our effect sizes and their associated standard errors. So we're going to really just be focusing on the problem of missing moderators. And so missing data, is going to occur, and it be for all kinds of reasons, which we're not going to get into, but they occur for all kinds of missing data occurs on the moderators we want to use in our effect size models. So moderators that are related to study characteristics, like participants or treatments or measures. And so to begin to answer the question of what is the appropriate analysis for missing data in meta-analysis, we need to understand the mechanisms for why we have moderators missing. So next slide, please. So let's start with missing completely at random. And let's imagine that one of the moderators we're interested in looking at in a meta-regression is duration of the treatment. We think effect size might, the size of an effect size might be related somehow to how long the treatment went on. So to assume that duration of treatment is actually missing completely at random, we need to assume that the primary studies that fail to report that moderator, that duration of treatment, fail to report that in a method that means that is completely at random. So those studies that actually observe duration of treatment are really just a random sample of our set of studies. And so that also means that the value of duration of treatment is not related, is completely unrelated to the missingness. So the question is, do we really believe that? And how do we know that? Okay, so that would be one assumption we could make. A second assumption would be missing at random, which is a slightly weaker assumption. Missing at random implies that the reasons that treatment duration is missing may be related to some other completely observed variable in the meta-analysis data, such as the effect size or some other moderator. This assumption is weaker than missing completely at random, but still problematic because how do we even know? How do we know if treatment duration is missing at random? And then finally, our last mechanism is missing not at random. And so here we're making the assumption that missing not at random assumes that the duration of the treatment is missing because of its value. So we may be missing values for duration of treatment more often when the treatment was short. But again, it's very difficult to know if any of these assumptions are appropriate. So next slide. So before we can even make a decision about the appropriate way to handle missing data in a meta-analysis, we really need to understand the nature of the missing data in that meta-analysis. So in this presentation, and my colleagues are now going to we're going to first talk about strategies to explore the missing data in a meta-analysis data set, including looking at patterns of missingness among our moderators and effect size data. And then we're going to go on to preview some ongoing work that we're doing on missing data in meta-analysis. So I'm now going to turn the presentation over to Karina.
Thank you, Terri. So as Terri was mentioning, those of you who had work on meta-analysis or conducted any systematic review or any kind of quantitative analysis, honestly, know that you're very likely to encounter missingness in your data set. And you could have an idea of how much data is missing or what variables have missingness by looking at your data, but techniques like exploratory missingness analysis help us to better understand missingness in our data and inform our decisions on how to handle missingness. So today I will show through an example exactly what kind of information you can obtain from this analysis and what kind of questions you can answer with exploratory missingness analysis. So here I have listed some questions that we may explore with EMA. So for instance, where information is very scarce, we may want to assess how much data is missing in each one of those covariates. We could also be trying to understand what should we think about bias of omitting cases and explore if missingness in one variable is related to observed values in another variable. Another question that we might be interested in answering is whether assumptions about missingness mechanisms, such as what Terri was describing, missing at random, missing not at random, and missing completely at random, are feasible or not in each one of those cases. Finally, we may want to know whether we can or should we be using meta-analytics methods such as complete case analysis, also known as least-wide deletion, which assume the data are missing completely at random. So with these questions in mind and using a meta-analytic example, I'm going to walk you through different visualizations and numerical summaries that can provide information to answer these questions. So here I have an example from Tanner Smith et al., who examined the impacts of substance abuse interventions for adolescents on subsequent substance use. So the effect size they use in this meta-analysis compares two different groups of studied participants, group number 1 and group number 2. And as you can see on this plot, the authors documented different characteristics about the implementation of the treatment, such as intensity and location, and also participants' demographic information for each one of those groups as well, such as ethnicity and participants' age. You can also notice that even though most of the data is observed, the author had to deal with missingness in their data. So if we could take a closer look here, we can see that this aggregation plot visualizes the amount of missingness in the data, where dark areas indicates cells in the data set that are missing. So first, we can explore the severity of missingness in this case, where we have 12% of the data missing. But you can notice that the missingness is mostly focused on covariates. Those that are highlighted here in the circle in red, since all the effect sizes and the corresponding standard errors were completely observed. Another thing that we can see here is that there's little information about treatment groups, particularly regarding group number 2. And even further, if we can take a look at the next slide, there are cases where some covariates are missing for both of those groups, group 1 and group 2. So now that we have a better sense of this example, we can explore further missingness in the data using EMA. This next plot that I'm showing here is what I call the variable missing plot. And it shows basically the amount of data missing by each variable in the data. So in this example, there are 10 variables with at least 10% of missing cases. And this is relevant because, as we know from the literature, missingness rates of over 10% can induce substantial bias. And as we are gonna see later on in this presentation, other approaches such as missing multiple imputation are actually sustainable when missingness is less than 40%. So we also know that the precision of meta-regression coefficients depends on the precision of the studies included in the analysis. So missing a variable for an effect estimate with a large standard error, which is a low precision, can potentially be less damaging than missing the same variable for an effect estimate with a small standard error. So identifying those variables and determining the amount of missingness they have can be very useful here. There's also a numerical summary that can be helpful, and it's called precision weighted percentage, which is the fraction of information in meta-analysis associated with effects that are missing any data. In this example, effects that are missing any covariate make up to 74% of the total precision on the data. So in the next slide, I have just like a summary for this plot, and I think which is why we think this might be relevant, is that this kind of information becomes relevant when deciding which variables we want to include or not in the analysis. So the second plot that I'm showing here is called an offset plot. And this allows to study missingness patterns. So the figure here shows different variables and indicates how many rows each of those variables is missing from. So the dots along the bottom panel indicate different patterns of missingness, which means that a given set of variables are missing from the same row. And the bars on the top panel show the frequency with which these patterns occur. So there are a couple of patterns we're mentioning here, and one of them is the first pattern, where much of the information about the treatment condition in group 2 is missing. But if you also look at the other patterns to your right, it appears that this pattern occurs in conjunction with other patterns. So if you can see the last pattern that on your right, you can see how some information for that group 2 is missing, but we also have information for group 1 and some demographic information about group 2 missing as well at the same time. So from what we gather here, it looks like one missingness in one variable is related to missingness in other missing covariates, which can be an issue for multiple imputation since the precision of its methods depend on observed variables. And if they are all missing at the same time, you might not have enough information to impute. Another point here is that if we were to use complete case analysis or list-wide deletion, we could lose many effect sizes and thus reduce our sample size. In the next figure, I'm showing how you can also use exploratory missing analysis to examine whether missingness in one variable is related to observed values in another variable. So this can give insight into the mechanism of missingness, which, as we know, is an important consideration for incomplete data analysis. So these comparative plots, density plots that I'm showing here, compare the density of effect size estimates and their standard errors when a covariate is missing versus when it's observed. In figure A, we're showing the relationship between the missingness in group 1 treatment intensity that was measured in hours per week and the distribution of effect estimates and standard errors. And so we can see that the effects estimates tend to be slightly smaller and have smaller standard errors when group 1's treatment intensity is missing, which is highlighted here in green, versus when it is observed, which is in purple. And so in figure B, in contrast, we're showing here that the effects for which the group 1 treatment duration is missing tend to be larger and have larger standard errors than the effects for which the treatment duration is reported. So there are two major takeaways from this plot. First, it looks like omitting effect sizes with missing group 1 hours per week intensity could lower the accuracy of the meta-regression. And then second, it looks like the missing completely at random assumption is not very feasible here, because in some cases, missingness is related to observed variables, which are the effect sizes and the standard errors. So next slide, please. Here, I have highlighted some of the visualizations and numerical summaries available for exploratory missing analysis, which were relevant to this example. But as you can see on this slide, there are several other plots and summaries that could also help answer questions regarding missing data. And here I'm including the link to a vignette that goes into more detail on how you would use these summaries. And also I'm citing our paper if you want more information about this. So far, we have shown you how EMA can be useful for understanding possible issues for analysis when dealing with missing data. And next, Jihyun will talk about current practices to handle missing covariates in meta-regression and some of the potential problems with these approaches that we should be aware of.
Thank you, Karina. Yeah, so Karina talked about EMA, and once we understand the missingness in our data, we need to choose how to analyze the incomplete data. To do that, we need to understand how its method will work, and we want to essentially make valid statistical inference even with missing data, especially to avoid bias. So in this presentation section, as Karina introduced, I'll talk about current practices, how it works, and if there is any potential problem with that. Yes, missingness problem is common in meta-analysis. According to a review by Tipton and colleagues in 2019, 45% of collected research synthesis reported missingness problem in their data. Next, among those studies, 86% of the studies used ad hoc approaches, such as simply just deleting missing cases. So as Terri briefly mentioned earlier, complete case analysis and shifting case analysis, so-called deletion methods, they are the most commonly used in meta-analysis when the covariates are missing. Complete case analysis is the same idea as listwise deletion. It deletes any effect size if at least one of the covariate values is missing. Shifting case analysis is the same idea as pairwise deletion or available case analysis. And if you have heard of shifting units of analysis in meta-analysis context, SEA is the same concept with that, but we named it as SEA to match with complete case analysis. When we are interested in multiple covariates, SEA fits a series of meta-regression models on one or subset of covariates, and each model deletes the missing values. Compared to the general missing data literature, the impact of those two methods has not been widely studied in the context of meta-analysis. So we have studied these two methods, specifically the conditions for unbiased or biased estimates with CCA and SEA, and investigated the possible magnitude and sources of bias in meta-regression. In this presentation, I will deliver what we found with the conceptual discussions. In more detailed procedures will be presented in our upcoming manuscript. Let's take a look at an example with single covariate meta-regression model. As the equation shows, suppose we have the effect size estimate T for study I, which is fully observed, and the covariate X that has some missing data. And we are interested in regression coefficients betas. When we use CCA, the biases in the intercept and slope estimates are generally that depend on three factors: missingness rate, the total variation around the effect size estimate, and the relationship between effect size T and missingness in the covariate X. The first two factors are pretty straightforward, and we can intuitively understand that the larger the missingness rates and the larger the variations, then the larger the bias will be. Let's look into the last factor closely in the next slide. To understand the last factor, I would like to introduce one concept, selection model, or in other contexts, it's called missingness model. This presents why the covariate is observed or missing. Here we define a selection model using logic model. So it defines the logic probability of missing the covariate is a linear combination of some factors. For example, effect size, T, or covariate itself, and also others. If you click one slide. Yes, so the last component we saw in the previous slide that represent the psi1, the relationship between T and missingness. So the estimates will be biased when the psi1 is non-zero. So when there is a relationship, and also the larger the bias, with the stronger the relationship. So then when the magnitude of psi1 is large. We can see that the role of T in the selection model plays an important role rather than just the broader classification of missingness mechanism. For example, whether or not we include X, the incomplete covariate itself here. In other words, whether or not the missingness mechanism is MNAR or MAR, it does not impact on the bias in CCA because the missingness is still related to T with psi1. This is actually consistent with the general missing data literature, where emphasizing the relationship between the missingness in predictor and outcome to discuss bias in complete case analysis. The next figure shows really just a general pattern of how those three components related and the potential range of bias in the intercept, in our example, Cohen's d scale. the height of the shaded area indicates the amount of bias in this figure. And as you see in the y-axis, it indicates the amount of bias. Next slide, we see the first factor was missingness rate. And on the x-axis, we see that as the probability of missingness in covariates gets large, then the bias also gets large. We see the higher height of that bias. And next figure, the second component was total variation around the effect size estimate. And each panel shows different amount of variation. And as we move upright, as the arrow points to, the variation gets large. So the bias gets large as well. And the third component was psi1. The color shows the magnitude of psi1 as you see in the legend on the right. For example, with the lighter color, when psi1 is 7, like yellow color, it associates with the larger bias than with the darker color, smaller psi1. So we see that in most of scenarios, the amount of bias is not something we can ignore. So next, let's move to shifting case analysis scenario. Here, let's assume we are interested in this model with 2 covariates, but both covariates are incomplete. So we decided to fit 2 separate meta-regression models, one with X1, another with X2. Let's consider the first meta-regression model only include X1 and we omitted X2. We found that there are 2 sources of bias in shifting case analysis, omitted variable bias and missingness bias. Omitted variable bias occurs because we omitted X2 in this first model. OVB depends on 2 factors. First, beta 2, the contribution of X2, the omitted variable, to the complete data model. And correlation between X1, the included variable, and X2, omitted variable. So those 2 factors are related to OVB. In the next figure, this graph illustrates the function of beta 2 and correlation between 2 variables on the bias of beta 1, which is the slope of included variable. So with the larger magnitude of beta 2 on the x-axis, so as we move from the 0, and the correlation between 2 variables, in the yellow line is the largest correlation between 2. And we see that the bias of slope gets large as 2 sources. And next, the second source in SEA bias is missingness bias that occurs because we delete missing cases in the model. And this is the same source as complete case analysis bias. Because the total bias in SEA is a combination of 2 sources, depending on the direction of the 2 sources, shifting case analysis may or may not be more biased than complete case analysis. So next figure illustrates this relationship. We see that the total bias in SEA, the top box plot, is roughly the sum of omitted variable bias, the second box plot, and the missingness bias. Here, because 2 sources of bias are in the opposite direction, they cancel out each other to show the total bias in SEA. Okay, the last thoughts. We need to understand the missing data patterns. Especially, we need to pay attention to the possible relationship between effect size estimate and covariate being missing. And we need to be aware of potential bias in complete case analysis and shifting case analysis. And lastly, we need to investigate the alternative missing data handling methods that have shown some promise for meta-regression. In the next section, Jake will more discuss about this.
Thank you, Jihyun. So Jihyun got the short straw and had to tell you all the bad news about the fact that, well, a lot of meta-regressions take place with complete case or shifting case analyses, and those are only unbiased under a very narrow set of conditions, and they can be quite biased under a much broader set of conditions. And I get to tell you the good news, which is there's something you can do about it. The broader statistical literature on missing data gives us a whole bunch of options, including full information maximum likelihood, or FIML, which actually has an implementation for meta-regression in the MetaSem package, as well as the good old-fashioned EM algorithm. But today I'm going to talk about multiple imputation, which has kind of become the state of the art for most fields dealing with missing data beyond meta-analysis. And multiple imputation has a number of great attributes. It's very flexible. It's available in a lot of programming languages. If you're a devotee of R and metaphor, there's a package in R called mice that does a bang-up job of multiple imputation. And all of these methods, I should point out, kind of assume that data are missing at random. Especially these approaches that are already coded in software. So for those of you who aren't familiar with multiple imputation, I'm going to kind of walk through what it is and its implications for meta-regression. So suppose we have a data set that looks kind of like the picture Karina showed earlier, right? Which is essentially each row in this box here represents a row in our data, and each column represents a variable. And let's say, to the left of this line are completely observed variables like our effect sizes and our standard errors. And to the right of that, that's our covariates. And a black spot here indicates that a covariate is missing. And what we've kind of harped on about for the last 30 minutes is it's kind of hard to analyze a data set that looks like this. But you know what's kind of easy to analyze? A data set that has no missingness. We can analyze the heck out of that. We've written paper after paper on how to do that. And so the way multiple imputation works is well, let's just fill in values, because if we fill in all these missingness points, then we have a complete data set. We know what to do. And instead of filling in these missing values willy-nilly, multiple imputation kind of forces us to fill in values that are plausible, things we think we would have observed had there been no missing data. And since we don't really know what we would have observed, the approach of multiple imputation is to fill in a bunch of different plausible values and analyze your data assuming those are the things you would have observed. So what it looks like is we take our original data set that looks like this and fill in a bunch of different values for what's missing. You can see sort of down here, we have these bright colors. Those are filled in values. And each of these little things down here represents a data set now with no missing values because we filled them all in. Those are referred to as imputed data sets. And so multiple imputation proceeds by taking our meta-regression model and fitting it to each of those imputed data sets, and then averaging those meta-regressions. The idea being that it's the same model, but you're fitting it to slightly different data sets. And the averaging, pretty much you average your coefficients and you do a slightly different average for your standard errors, but this has all been pretty well hashed out in the statistical literature. The good thing about this, because this looks a little bit daunting, it looks like there's a lot of computations involved, you can do all of this in like 3 lines of code in R. It's not an overly onerous add to your current workflow. So there's a couple of things we need to keep in mind if we're going to apply multiple imputation to meta-regression, which is not particularly common at this point. The first consideration we should kind of keep in the back of our heads is the number of imputations. How many times are we going to fill in missing values? On this slide, we've got 5, but I didn't have to stop at 5. I could have done 10 or 100 or 10,000. Would have been a pretty busy slide, but I could have done it. So the question is, how many is too many? How few is too few? The statistical literature and indications from simulations suggest that a sweet spot for multiple imputation is somewhere between 20 and 50. That's not a gospel. I think there's going to be some wiggle room in there, but simulations suggest that when you're doing more than 50 imputations, you're not recovering quite as much information as you think you are. There's a point of diminishing returns, and south of 20, you're kind of leaving some meat on the bone. The second big consideration is that there's actually two stages of modeling that go into multiple imputation. There's our analytic model, which is just our meta-regression model. It's the model we would fit if there was no missing data. And that's a model we really understand. But there's also an imputation model, right? And an imputation model refers to the process by which we fill in these values. I said it wasn't willy-nilly. We actually use a model to fill in missing values, to impute them. So what does an imputation model look like? It looks something like this. Suppose this is our data set, and in this red box here, we have our effect sizes and a whole bunch of covariates. And in our blue box, we're like, let's try to impute this one missing value. So an imputation model would regress this covariate of interest, let's call it X, on, let's say, everything else in your data. And when I say regress, I mean that in the broadest possible sense. If X is continuous, you might use a linear regression. If it's binary, you could use logistic or probit regression, but you don't have to limit yourself to the GLM playbook. You could use stuff from machine learning like classification and regression trees or random forests. Or gradient boosted machines. But the key idea is you're going to regress X on everything else and use that model to guess at what you would have observed. You can do the same thing with a different X, just regress that X on everything else. You could do it with a different X. You could cycle through all of the variables that are missing. And so the point here is that you can actually specify an imputation model for each individual covariate that's missing to ensure that you're filling them in with the most accurate or the most predictive values. So what does this mean for meta-regression? Because this is a general consideration. What are the things we need to think about when we're applying this to meta-analysis? Well, the statistical literature tells us that multiple imputation is really good. It reduces bias. It gives us the best standard errors if our imputation models have the following three properties. If our models are really highly predictive, if they account for things that are related to missingness, and if they're compatible with our analytic model. Taking these one at a time, if we want models that are imputation models that are highly predictive of what we would have observed. And so if you're going to use multiple imputation, it probably helps you if you set up your imputation model using as many relevant predictors as you can, as are feasible, that are highly correlated with your variable you're trying to impute. And I think where possible, use flexible imputation models. In other words, get away from the GLM framework and use something like nearest neighbors or random forests or something like that. And the nice thing is there's some ability to do that in a lot of software. The second point is that it's probably a good idea to include variables that are related to missingness. And how would you know a variable is related to missingness? You do the EMA that Karina showed you, right? You'd look at plots that correlate missingness, in a covariate to, say, your effect sizes. The third point is this actually a really refined mathematical point called compatibility. And what compatibility means is in an imputation model, you're taking variables, including your effect sizes, and saying something about a covariate. And then in your analytic model, you're turning around and using that covariate to say something about your effect sizes. And those two models in mathematical terms should imply there's some big joint distribution that exists for your data. And really what that means is that there should be some mathematical link up between your meta-regression model and your imputation models. So the good news is that points 1 and 2 are at your fingertips. Almost every multiple imputation software that I can think of lets you specify how you want to impute your variables, which means it's up to you to select which covariates, which effect sizes you want to use. what sort of algorithms you want to use. And the nice thing is that it doesn't add too much to your workflow. And as long as your computer was built after the year like 1996, it should be able to handle some of the computational load. The bad news is that compatibility for meta-regression models is not a thing in multiple imputation software currently. But it's coming soon. All of us who are giving this talk today are currently working on this. And so it's coming, and you might be wondering, well, before I start seeing software from these folks, should I even bother with multiple imputation if I'm only going to get 2 out of 3 here? And the answer to that is absolutely yes. Even if you're not using compatible imputation, you can still really improve the accuracy and precision of your analysis. So this is a figure based on some simulations Jihyun and Tasha Barefis have been running. It assumes you've got 100 effect sizes, 20% missingness, not a lot of residual variation. And in all of these simulations, Jihyun applied a complete case analysis, a shifting case analysis, multiple imputation, and this other thing, FIML, that I mentioned earlier. And here is the relative bias on the y-axis, and on the x-axis, we have different methods. The blue box here is the shifting case and complete case analyses. The red box here is multiple imputation, and a relative bias near 0 means we have unbiased estimates. A relative bias near 1 or -1 indicates that the bias is as big as the parameter itself. It's like 100% bias. So what we can see here is a complete case or shifting case analysis can be super biased, multiple imputation, way less biased. You will help your analysis a lot by using multiple imputation. And this is one plot in a paper that Jihyun's writing that has a whole bunch of plots that show this, right? It shows that in a whole bunch of conditions, whether there's no residual heterogeneity, which are the first 2 columns here, or a lot of residual heterogeneity, which are the second 2 columns here, whether the missingness is 20% or 50%, which are the first and third or second and fourth columns respectively, or if we have 20 or 100 effect sizes, multiple imputation is going to wipe the floor with listwise or pairwise deletion. But I think we should point out it doesn't get you to 0 for bias. And work that we're all doing is suggesting that compatibility can further improve this. So Karina, in her dissertation, ran a whole bunch of simulations that compared incompatible and compatible imputations. Here we see 2 different types of missing at random mechanisms. We see the bias in absolute terms. I'm assuming, correct me if I'm wrong, Karina, that these are on the scale of Cohen's D. For random forest imputation, nearest neighbor imputation, both of which are pretty easy to set up in R's mice package. And then compatible imputation, because she was able to write a nice little function to do that. And what you see is that as our missingness gets a little bit bigger, multiple imputation that's compatible will have less bias. All of these, we should mention, will have less bias than a complete case or shifting case analysis. And so taking a step back here, I think there's a few things we want to hammer home. If you remember nothing else from this talk, the next couple of slides are the things you should take away for your own analysis. The first thing is that you should absolutely do an exploratory missingness analysis. You should do that for your meta-analytic data sets. You should do it for all of your data sets. If you're encountering data in the wild, you are encountering missing data. You should check missingness rates. In meta-regression, you should check the amount of missing precision. Are big studies more likely to be missing data than small studies? And then check missingness patterns. And I think it's usually a good idea to look at the relationship between missingness and effect size estimates, because that's going to drive a lot of the bias in analyses. We should probably stop doing complete case and shifting case analyses. Jihyun showed that there are very narrow sets of conditions under which these give unbiased estimates. There is a large set of conditions under which these give very biased estimates. And so you might get lucky, but I don't think hoping you get lucky in your analysis is an approach that we should be endorsing. Lastly, instead of doing a complete case or shifting case analysis, you should do something else. That something else can be FIML, there's the Meta-Sem package, or it could be multiple imputation. If you use multiple imputation, you will almost always do better than your complete case or shifting case analysis. And so for us, and I'm speaking kind of on behalf of my friends up here, I think a good workflow for meta-regression is to start off with an EMA, use the results of that EMA to inform your multiple imputation, run your multiple imputation, and then analyze your data. And so if you're an R user like me, you want to use mice, pair that with metaphor. I think Wolfgang's on the call and he's done some nice things to make those two packages compatible. And then of course, if you've got a dependent effect sizes, you probably should adjust for that. And the only thing that's really subject to change in this pipeline is that we're working on methods to make the imputations compatible, and therefore our analyses a little bit more accurate. So coming up soon, hopefully. And so with that, I think we'll conclude. Thank you to my friends and colleagues here that gave this talk with me, and to James for organizing this, and for everybody for listening. And I think we can dive into some questions and answers.
Great. Thank you very much to Terri, Karina, Jihyun, and Jake. We've got some time for questions and discussion. So anyone in attendance is welcome to post questions in the Q&A feature on Zoom. Post them in the chat, and we can read them aloud. Or I think there's a raise your hand feature for all attendees, and we can call on you if you'd like to ask the question live. So the floor is open.
I can read the questions out loud. Danny Swan has a question. Are there any important or notable scenarios where MI is going to provide substantially worse bias than CCA or SCA?
I think Karina and Jihyun can refine some of this because they've done a lot more simulations than I have. It's rare, is my experience. Rare enough that I would not worry about it typically. Jihyun or Karina, do you remember any of the conditions that MI was sort of losing out to a complete case analysis?
In my simulation study, when I have only one single covariate in a meta-regression model, so that means in the imputation model, I only have effect size itself or the standard error to use as a predictor in the imputation model. In that case, compared to when I have more covariates in a model, so I can add more information to the imputation model, it performed worse, like similar to CCA, but some scenarios smaller. But yeah, generally, that's why we encourage to use more covariates in a model so that we will have more information to use.
Yeah, same in my simulations. Complete case analysis in most of the scenarios perform worse than multiple imputation. It was only when I was trying out, because eventually I decided to go with a multiple imputation model that was, in a way, I'll say, include all the covariates available. And so that's something that Jihyun was talking about, right? So like if your imputation model is not super precise and you're only including 2 covariates in it, then you don't have a lot of information to impute what is missing. And so in those cases, maybe it's gonna perform worse or similar to complete case analysis, but otherwise, you're better off using multiple imputation.
Another question by an anonymous attendee is, can we also reproduce data and wrapper functions in the vignette link? So do you have like the data in a GitHub site that they can source?
We do, I'm not sure if the data is available in the GitHub.
I think it is. So the tutorial is really just a presentation of a HTML file in a Git repository. The data, the wrapper functions, and heck, our markdown file that we use to generate it, those are all available in the same Git repository.
Next question by Elif. How can we convince the reviewers that multiple imputations produce less biased results?
That's a tough question because not all reviewers are convinced by multiple imputation. I think a really nice resource to cite is Little and Rubin's textbook of statistical analysis of missing data, where they walk through how biased a complete case analysis is and show theorems that multiple imputation can reduce bias in a lot of different statistical analyses. That's I mean, if you've got Don Rubin on your side in statistics, it's probably a good sign.
You could also eventually cite Jihyun's paper.
Exactly.
Going to be published soon.
Really hard, like work hard, like fast to make publish. It's under revision right now.
Mm-hmm.
So when it becomes like publish it, then you can cite that.
Yeah, and eventually my dissertation as well. So there you go. Coming soon. We're working for you guys.
You should cite all their papers. Another question from Carlton. I may have missed this, but would there be substantive differences in the impacts of multiple imputation for SMD metas versus correlation metas? Standardized mean difference metas.
Well, I think that depends on how you're meta-analyzing your correlations. If you're taking your Z transformation of them and put in sort of stabilizing the variance in the distribution of the correlations, the behavior of multiple imputation should be relatively similar between standardized mean differences and correlations. If you're doing a raw correlation meta-analysis, I would maybe ask you to transform them because the variance is stabilized a little bit. But I think there would be some impact there. It's something that you probably have to account for in your imputation models.
We have some questions in the chat. Can you go from Philippe? Can you go further into what is compatible imputations? Can you give examples of compatible imputations outside MA just to learn how this can be done? Can you explain a little better what is compatible? Yeah, I think it's the same thing twice.
Yeah, it's a can of worms. And Karina, Jihyun, Terri, jump in as I start drifting here. So compatible imputation essentially is this, especially, and it's discussed a lot in the context of missing regressors in a linear regression. So whether that's a meta-regression or just a good old-fashioned OLS or logistic regression. The idea is you want a good imputation model that's predictive. And if you're missing a covariate, presumably you'll use an outcome to impute that because those have to be related because that's why you're fitting this model to begin with. And so if you're going to use an outcome, a dependent variable in your analysis to impute a covariate, you're assuming a specific conditional distribution of your covariate given your dependent variable. Then you're going to turn around in your analysis and assume a different conditional distribution of your dependent variable given the covariate you just imputed. And so you have two conditional distributions here. You've set them up separately. They don't necessarily need to imply an actual joint distribution that exists. Compatibility is the assumption that they exist or the proof that that exists. So there is some research that came out in 2015 that showed that if you want to generate compatible imputations for a linear model, the model you use for imputation has to be, the likelihood in it has to be proportional to the likelihood in your analytic model. In other words, you kind of stuff your analytic model into your imputation model. How you do that requires a little creativity. That's something that Karina, Jihyun, and I have been kind of playing around with meta-regression. So it's a super technical aspect of it, but it's something that I think we've seen can help improve analyses. Karina or Jihyun, I think you should probably say just a little something extra because you guys.
Yeah, I guess I just wanted to say that for the meta-regression example here, when we think about compatibility and incompatible models for multiple imputation, we're basically just taking into account the fact that meta-regression uses weights for precision, right? And so if your multiple imputation method is only using linear regression models to impute, then you're not accounting for that weighted precision that in meta-regression is doing. So the fact that the whole idea behind making this compatible is that you're accounting for that. So like your multiple imputation method, it's more similar and it's accounting for that as well, that your analytic model is doing too, right? So like, that's like the idea behind compatibility. I guess, I hope that helps to understand. Yeah.
Steve in the chat asked a question also about compatible multiple imputation and its benefits compared to the regular MI process, but I think you answered most of it already. Next question by Philippe. Does the FIML approach have less resistance in publication process?
I don't know. I don't think the field knows, because most of the meta-regressions that are being published are based on shifting case or complete case analyses. What I can tell you is the example data that our vignette is based on, that Karina presented, they use the EM algorithm. So it's hard to say how much resistance you're going to get from reviewers for different things. I think the thing to keep in mind is that there's a whole host of statistical literature beyond what we're talking about that says that these are pretty smart things to do when you're doing an analysis with missing data. And the big thing to keep in mind is that you need to account for why your data are missing and how you're going to analyze your data.
And just a little add note, when you decide to use FIML, you need to remember that like using FIML based on SEM framework in meta-analysis, that's a like whole different parameterization of your model. So it's like your research question may be different than your original one. So that's also one thing to keep in mind, yeah.
We have two more questions, but I think we're at time. I don't know, James, you want to?
Maybe we can just do the one last question from an anonymous attendee. And I'm indulged because I was wondering about this as well. So do aspects of your data structure, like using multiple outcomes or having multiple measures over time, so affect how you would approach using multiple imputation? Is it a sort of a situation where, like, you know, even doing something that doesn't quite fit the structure is better than nothing, or should we be worried that we're mucking things up because we've got like a longitudinal or multi-level structure, but we're not accounting for that in the imputations?
Yeah, that's a good question. I mean, my dissertation was about compatible imputations for multi-level model meta-regressions, basically. So like when you do have this dependency, and so the whole compatible idea also translates to this other features as well. So if your multiple imputation model is not accounting for that dependency, then it's not going to be as good as it will be. But I'm pretty sure, and this is based on my own work, I found that even though I was not accounting, even though I was not using compatible imputation for those multi-level meta-regression models, the multiple imputation was still better than complete case analysis and shifting units of analysis. So yes, it's relevant, but then the simulations that I was able to perform show that multiple imputation, still not accounting for that compatibility factor, was still better than complete case analysis.
Great, thank you. I'm afraid that we're out of time. So I'd like to thank all of our presenters one last time. Dr. Terri Pigott, Jihyun Lee, Dr. Karina Diaz, and Jake Schauer. Our next entry in the seminar series will be on November 19th, when Dr. Brenton Wiernick will be presenting on modeling statistical artifacts in meta-analysis. So this is particularly relevant in meta-analysis of correlations, where there's concerns about the reliability of the measurements that go into the correlation estimates. And do watch the website, watch our Twitter account for follow-ups on this on this presentation. And thank you very much for coming. Cheers.